So far, we have discussed about the beams. What is the definition? What is the shear forces acting over a beam? And what is the bending moment acting over a beam? And we made the shear force diagram and bending diagram, which shows us the variation of shear force or bending moment across the length of the length of the beam, which is used as an abscissor, and where shear force or bending moment are used as an ordinate, positive or negative, according to the result itself. Next, we used the bending moment to find out the bending stresses in different section of the beam itself. How this is why it is required. First, we know we have to use the bending moment across different section of the beam itself. In the process, we have deduced a bending moment equation which gives us what is the bending stresses induced in different section, which depends on the induced bending moment in across all these sections itself. In that particular lecture or discussion, we have discussed that the bending moment across a section, across two adjacent sections where they are away by a elemental distance like dx, means almost they are of the same section but not exactly the same, but they are away by a impedance distance area. Here we have discussed that the external load, first of all, is the distributed load, but supports are point are they are simply supported, and as they are distributed, even for a infinitesimal length dx, we have the external load acting over the beam itself. But at that moment, we have assumed that no shear force or vertical force acting over that infinitesimal element, which is of thickness only dx. Only the resultant bending moment, which is created over it, is we have used and find out the neutral point, neutral line, and neutral plane over which there is no forces acting, no bending stress, tensile or compressive forces acting, which is totally neutral, and their length is not changing. Even the sheet is bent. The bar is bent itself. But actually, the theory, there is no shear stress acting on the section, but or all the vertical forces acting on that elemental section is negligible. As a theory, it is okay, but it can happen in sometimes. Along with the bending moment, it has all this elemental length has a considerable amount of shear or vertical forces acting over this section concerned. What this section which are away from each other by a distance dx or differential distance dx. So we have to find out when the shear force is not negligible, but then we have to find out in the design criteria. So you have to find out what is the shear stress induced in the bending moment in this particular section due to the action of this vertical shear force acting along this section itself. So here we are doing again the same process. We are having a beam which is have a distributed load over it. Distribution is uniform, not any non-uniform. It is uniformly supported at this end, and we are considering two sections AB and CD, which are infinitesimal away by infinitesimal distance dx, with only a dx itself. Now we know that neutral axis, constitutional neutral axis, as it is a rectangular section of the beam, the neutral axis goes through the CG and as the centroid of the beam itself like this. What we are doing now, we want to know the shear stress across any line or stress or any fibers which is away by a distance y from the neutral axis, and which is topmost upper part of the y, where it is subjected to the compressive bending stresses, and we have to find out what type of shear stresses acting over this section itself. No, what we are doing here, first of all, we are finding the beam, home is loaded, information, etc. What I have just told you. Let's M is the bending moment at the section A, AB, and M plus dm is the bending moment at a section CD. We are assuming due to the elemental distance between the two adjacent section, bending moment is also changing by an amount equal to elementally infinitesimal small, but it exists. M is not equal in both the adjacent section. There, one of them is M, another is M plus dm. M is acting over AB, and dm is acting over M plus dm is acting over CD itself. At the same time, we are assuming that shear force is not negligible across the section AB. It has certain value. So shear force acting over the section AB is defined as the is defined as the shear force F. And shear force acting over the adjacent section CD is not equal to that of F, but is changed different by an amount infinitesimally small equal to df. So shear force at CD is equal to F plus df itself. Now bending moment. Now I is the moment of inertia of the section about the neutral axis. Now consider an elementary strip at a distance y from the neutral axis as shown above. Let what is seen here, it is at a distance y. This is shown here, which is from this is the neutral axis is written as NA, and we are considering strip at a distance y from neutral axis itself. Now let sigma, the intensity of bending stress across AB at a distance y from the neutral axis itself. This bending stress is supposed to be compressive in nature because it is at the upper portion of the bending moment, upper portion of the neutral axis itself. Small a is the cross-sectional area of the strip itself. We have discussed that from the bending moment equation, bending stress equation, m by y is equal to sigma by y, or sigma is equal to m by y into y itself. Similarly, there is a change in stress. Similarly, in the adjacent section CD, thus this stress due to the change in this bending moment from m to m plus dm, the stress is changing from sigma plus d sigma itself. And y is same for both this section, and moment of inertia is same for both this section, as both are truncated from a rectangular beam itself. Just a second. Now, well, sigma per d sigma is the intensity of bending stress across CD. Now we know the force acting on area AB, total force, stress multiplied by the area itself. And stress is sigma here, and A is the area of the cross section here. What is the area of cross section? How it is resolved? Just I'm showing you again. This is the cross sectional area of the strip. Means if there is a strip here, it is not very clearly written, but considering there is a strip, it is the cross sectional area of that particular strip itself. Now, so the stress acting over the strip is always sigma. We have decided the intensity of stress across the section AB is equal to sigma into A. It is the strip is active over the area. We put the value of sigma here, m by I into multiplied by y into a, where y is the distance of the strip from the neutral axis itself. Similarly, the force acting across C, sigma plus d sigma into A, as the stress is not area is not changing, the strip remains same from section to section itself, but force is changing from sigma to d sigma. So force sigma plus d sigma multiplied by A is equal to m plus dm by I into y into A. M plus dm by I into y into A. So the net unbalanced force across the acting on this elemental strip, elemental force is a sigma minus dm by I into y minus y into a minus m by I into y into a, dm by I, or that is equal to dm by I y into a itself. So the total unbalanced force above the neutral axis we can find out by integrating the above equation between 0 to d by 2. Well, d is the half of the height of the section of the cross section, where we are just considering that a is the distance of the a is the area of a strip of the cross section over the area over the neutral axis, above the neutral axis. So what is the distance? We are integrating the distance from 0 to d by 2. From 0 is the position from the neutral axis, and d by 2 is the maximum distance, means outermost area of the strip itself, outermost area of the beam itself. So if you integrate 0 to d by 2 dm a y d y, we will get the resultant unbalanced force across the section from neutral axis to the uppermost layer of the beam itself. I repeat, if we integrate, here we are having the difference in of the difference of the bending difference between the bending stress across the section, across to adjacent section itself, and next unbalanced force of the strip is equal to dm by I y into a. Now it is for only on a strip which is acting above the neutral axis. So we have to know the total unbalanced force above the neutral axis. We have to integrate this equation from the distance of the neutral axis, and from at neutral axis the distance is 0, and at the outermost section of the strip is from neutral axis is d by 2. So dm into yi is equal to a into y by y into dy, or dm, the change in bending moment, and divided by I, the moment of inertia of the strip, it remains unchanged between the section AB and SC, because we already considered this is the change in bending moment, and it is remains unchanged from the neutral axis to the outermost layer of the beam itself, because this dm is the difference in bending moment from left to right of the beam itself, left to left beam, left section AB, and to the right of this section BC. So dmi is constant, it's brought outside the sign of integration. So integration is being done from 0 to d by 2 for a product A, which is the cross section of the area of the stick, y the distance from the neutral axis, and dy is the our set of integration itself. So this will become dm by I into a. A is the cross-sectional area above the neutral axis, total cross-sectional area, but not the total cross-section of the beam, because we are saying that beam is at the central part of neutral axis, what is situated at the center of the beam. So this is the half of the area of the cross-section itself, and but it is the total area of the beam above the neutral axis. So we put the A here. This is as we are integrating from A to d by 2. So this is A is the area of the beam above the neutral axis multiplied by y dash, the distance between the center of gravity of the area and the neutral axis. Means there can be a number of different areas throughout the length, throughout this cross section from neutral axis to the topmost end, and the distance is the this which is the summation of sigma dy is the distance between the CG of the area and the neutral axis itself. All this force will pass through the center of gravity of the area, and we are finding out the CG of the area and find the distance of the CG of area from the neutral axis itself. So know that intensity of the shear force is tau, total force divided by area. We are total force is given as dm by total force is given by dm by I into a y dash, which is already you have calculated, divided by the area itself. The area is the width of the beam and dx is the thickness width of the beam and dx is the height of the difference distance between the two beam itself. Hmm. Where dx into b itself, where b is the width of the beam, then dm by dx a into y, this equation becomes dm by dx uh, dm by dx a into y dash divided by I into b, a into y dash by I into b. Dm by dx, we know the rate of change of bending moment is equal to the shear force F. So we put the value of F here and multiplied by a into y dash. A is the cross-sectional area of the beam above the neutral axis, multiplied by y is the distance of central gravity area above the neutral axis from the this area of the area above the neutral axis to the neutral axis, and I is the moment of inertia of the entire beam, and b is the width of the beam itself. So thus we have got the shear value of the shear stress, here stress in the beam itself in terms of the shear force, area half the area of the beam, y dash is the distance between the central gravity of the area of the beam, the moment of inertia of the beam, and width of the beam itself. Now let us use this equation in further. We had already decided an equation which gives us the determine the value of shear stress. Well, here we got this equation which gives us the value of shear stress at any section of the beam itself. But along the depth of the beam, what is the value variation of shear stress? Here, because here the depth of the beam is along the depth of the beam from the topmost to the neutral layer is given by the y bar, which the distance of the CG, or the distance of all the fibers we can imagine from above the neutral axis to the topmost fiber itself. And we will study this with the shear force along the depth of the beam. So as if we go through the individual shear force distribution, by ignoring the value of y bar, which is the value distance of CG, then we'll have the distribution of shear stress along the depth of the beam itself. For doing so, we should calculate the intensity of shear stress at important section. So shear stress we have to find out at all the important section of the beam, then sketch a shear stress diagram. Such a diagram helps to enumerate the value of shear stress at any section along the depth of the beam. So here, next problem we want to go through, what is the intensity of shear stress at the important section of the beams, and then we have to find out the shear stress diagram, so that this diagram gives the value of shear stress at any section along the depth of the beam itself. Let us go through that. Now, let us go through this process, you can say, not the problem. Distribution of shear stress over a rectangular section itself. Consider, however, rectangular section. This is a rectangular section taken from between two sections A and section AB and section CD. And this is the neutral axis of the beam itself. And this is the width itself. So what is the what is the difference between shear stress? What is the distribution of the shear stress from AB to CD, and how it is increasing and how it is reducing? Let us go through it. Now, uh, we know the shear stress, just we have proved that at any section away from Y is given by tau F multiplied by A into Y bar divided by I into B, where Y bar is the distance of CG from the neutral axis of any section of the total area itself. Here we have to use this formula because this Y bar is not our requirement, because Y bar is the distribution of the distance of CG of the entire area above the neutral axis. Here we want to know a particular section, so Y dash will not our point of consideration. Next, F. F is the shear force at the section A. A is the area of the section Y, that is this is the A, capital A, area of this section Y, shaded area AJDK. So this is the area. Y dash distance of the shaded area from the neutral axis. Actually, this will be uh, hmm, distance of the shaded area of the CG of the shaded area from the neutral axis itself, and A Y bar, the moment of the shaded area about the neutral axis. Distance of shaded area, or you can say the if there is a CG somewhere at the central part of this rectangular section, the distance of that CG from the neutral axis is given by Y dash, and A into Y dash, A is the area, and multiplied by that distance of the CG is the moment of the shaded area about the neutral axis, because we are using the distance of CG from the neutral axis itself, and we are using the area of this shaded section A. So A by 1 the moment of this shaded area to the neutral axis. Now the moment of inertia of the entire section from here to here, here to here is the I. B is the width, means distance between the two section itself. In case of y, x, dx, we are saying here, this is the width itself. We know that the area of the shade, what will be the, let us find out the area of the shaded section AJKD. Let us find out the area of it. It is clear that width is the, B is the width, and the height of the area will be D by 2, means from here to here minus the distance given here, the distance of the line JK from the neutral axis. So D by 2 minus half. So plus we have to Y plus D by 2, half of D by 2 minus Y. Y, the distance, half of D by 2 minus Y means the half of this distance between dk or dj. So y plus d by 4 minus dy by 2 is equal to y by 4 plus dy by 4. So half y plus d by 2 is the distance of the CG of this shaded beam. So substituting this value of a and y bar in the equation, what we are saying, f plus a into y bar is equal to I into b. B is the width between these two sections, and so put the value of a, put the value of f is as it is, put the value of a, b into d by 2 minus y, and put the value of y bar, which is half d y plus d by 2 divided by I into b. Then if we simplify further, if we multiply them between them, d square by 4 minus y square, and f, this b will cancel this b itself, and f divided by 2i, this will come out if we d square by 4 minus y square, and b is cutting out. This is the f divided by 2 into I divided by d square by 4 minus y square itself. From the above equation, The tau measures increases as y decreases. From the above equation, tau increases as y is decreasing itself. That is, this 2 is coming. This half is 2 is coming here. From the above equation, tau measures as the y decreases, and at a point where t is y is equal to d by 2, tau is equal to 0. T by y, where y is equal to where y is equal to at the outermost stage. Here tau is equal to 0. And y is equal to 0, tau is the maximum. Then y, where y is the 0, tau is the maximum itself. So means at the neutral axis, we have the maximum value of the tau with respect to y. And this is a moving, this made in terms of a parabola itself. Substitute y is equal to 0 and I is equal to b into 2 to the power 12 as for the moment of inertia about the rectangular section. In the above equation, we will find f divided by 2 into d into 2 to the power 3 by 12 into d square by 4, or 3 into f by 2 bd into 1.5 multiplied by 3 into f by 2 into bd equal to 1.5 tau average, where tau average is f divided by area, f divided by f in b into d itself. This is the width and this is the depth itself. The distribution diagram thus becomes like this. Here it is 0, here it is 0 is the maximum at the neutral axis itself. Now we have calculated the distribution of shear force of a rectangular section. Let us now calculate what is the shear force at triangular section. Process is same. Now consider a beam of rectangular cross section A, B, C, and its base is B and height is B and height is H. Now and tau F multiplied by the shear stress over this particular section is F multiplied by A into y bar divided by IB, where you have to know the shear force at the section. What is right there? A into y bar is the moment of the shaded area above moment of the CG of the shaded area above the neutral axis, and I moment of inertia of the rectangular section above the neutral axis, triangular section above the neutral axis itself. Means this one. I is the moment of the triangular section above the neutral axis. If neutral axis somewhere here itself. We know that width of the strip JK is given by B equal to B into X by H, where B this length JK divided by B, length JK or divided by B is the height of the area that is equal to X, and it is divided by the height of the area that is equal to H itself. So from the similar triangles, it is available from the similar triangles AJK and ABC itself. So the area of the portion AJK is half the base, that is GK into X, half BX by H into X, that is BX squared by 2H itself. Now y dash, what will be the y dash? Y dash is the distance of the CG of any section considered from the neutral axis itself. Here y dash will be 2 into H by 3. This, the position of the neutral axis will be CG somewhere from CG here, and from the CG of this triangle A, B and H is 2 into H divided by 1/3, and the CG of this particular shaded area is 2 into X divided by 3 itself. So we have to uh, eliminate this second portion from the first part to get the y dash. The distance of CG of this section is equal to 2 into 2/3 h minus x. Now you substitute the value. We got the value of a, got the value of y dash, and got the value of b. So in the equation of tau, we put f, I put all these values, f multiplied by bx square by 2h plus, which is here, the area, plus multiplied by 2 by 3 into h by minus x. It is the area y itself divided by I multiplied by the width b into x by h. So thus I into 3, f divided by 3 into I, where f and I is here, f into the numerator, I is in denominator, and we have this 3 point of keeping out. So bx square divided by h is equal to 2 into h square into h square by into hx. So that after elimination of all these things, it will become x into h minus x. Thus, the value of tau is equal to f divided by 3i hx minus x square. This is the equation of the shear stress of a rectangular section of a beam. Now, the variation of the x is with respect to x is the parabolic variation. We see that at a point where x is equal to 0 or at a point where x is equal to h, tau is equal to 0. So x is equal to 0 means what is x here? Just show it. I'm showing it again. What is the value of x here? Yes, if we consider the cross section, is the height of the section AJK. Now, so the variation of x with respect to x, or the height of the section, is parabolic, and where x is equal to 0 and it is only a point, and x is equal to I, tau is equal to 0. Both x is equal to 0 and x is equal to h, tau is equal to 0. At neutral axis, where x is equal to 2 into h by 3, 2 into h by 3 itself, we put the value of h and say, do that calculation, necessary calculation itself. We'll find that the area will be 2 into f h square by 27 bh cube by 36, which is also reduced to 2 into f by 36 3 bh. So 4 by 3 into xy area is 1.33 tau v. So tau, the shear stress tau is the value of average shear stress multiplied by 1.33. Now for a maximum intensity, that is the value of maximum intensity here. How will you get it? We have to differentiate the equation 2 just to have an page equal to and equated to 0. So d tau by x 1 f by 3 h x minus x square equal to 2, or if we make the calculation, differentiate them, this f 3h are all removed, and hx will be h and x square will be 2h. H minus 2x equal to 0 or x equal to h by 2. Now substitute the value of x, substitute the value of the width, and for the maximum shear stress, if we put this will be equal to h square by 2, h by 2, and after simplification here, we'll get 3 into f by b into h, or 3 by 2 f divided by area, or 1.5 tau higher. The shear stress thus This is the shear stress distribution which takes place in this particular triangular area itself. Okay. Next day I will go for this portion, distribution of shear to other type of section like IT section like this. I'm stopping the share and thank you for attendance of the class and thanks for your patient hearing. Goodbye.